Welcome to this video. In these sessions, we will talk about Miller indices of planes and directions in crystal structures. And we will see why they are important, means why Miller index is important, why planar density is important for us, and how they define families of planes and how planar density is calculated in different structures, such as FCC or face center cubic and BCC or body center cubic crystals. Then we will connect these property, means planar densities, to slip systems, especially in 111 plane groups and 110 directions family systems in FCC, and explain how these concepts related to dislocations, plastic deformations, ductility, and brittle behavior that we have. Okay. What are Miller indices? Miller indices shows in parentheses and by some numbers, H or K or L, that we substitute instead of them, that describe the orientations of plane in crystals. Why they are important, what we should calculate that at first. For calculating that, we should focus that this plane that we are considering passes through the selected origin or no. For example, if origin was this point, oh, sorry. We cannot consider this point. Why? Because this blue plane passes that, so we should consider another plane. So I considered another origins, and this origin is O. And you see that the blue plane doesn't pass the selected origins. The next step, read of the value of intercept of this plane with x-axis, y-axis, and z-axis. So, for example, this intercept is A, the intercept here is B, and the intercept of z-axis, we don't have that, and it is infinity. So x-intercept is A, y-intercept, for example, is B, and z-intercept here is infinite. The next step, take reciprocal of intercepts such as 1 per A, 1 per B, and 1 per infinity, that is 0. The next or fourth steps, normalize reciprocal of intercept by multiplying by lattice parameters. What is the lattice parameters? For example, the dimensions I show by different color. The dimensions of this cell in x-axis, for example, is A, in y-axis is B, and z-axis is C. So multiply this in A, in B, and it's C, because the dimension of cell or cubic structures in z-axis. Okay, AA is 1, it's 1, and it is 0. So for this specific plane, it is 1, 1, 0, and 1 is H. 1 again for this case is K, and it is 0 is L. And the next step reduces to the smallest integer values, that for this case we don't need that, all of them is whole number, and enclose resulting Miller indices in the parentheses, no comma, anything as HK. Why do we need Miller indices? Okay, first, define and classify the planes for crystallography. For example, here, I want to add some tricks that if you see something 0 in plane, for example, here is 0, 0 here, means parallel to x-axis and y-axis only intercept z-axis at 1. This blue plane that you see that, for example, in this case, it is x-axis, it is y-axis, and it is z-axis. And you see that this blue plane, parallel x, parallel y, only intercept z-axis, that reciprocal of that, and normalize that, it should be 1, okay? For this case, you see that it is parallel to z-axis, so z should be 0. It's parallel to x-axis, to y-axis, because x-axis here is this. Y-axis is 0, only intercept the x-axis. So after knowing the trick for finding the Miller indices and using 0 and parallel or something, why do we need Miller indices? Define and classify planes for crystallography. Predict the directions of slip and plastic deformation. In next slide, I talk about that and related that slip and plastic deformations to planar density, or PD, that we have for planes, and linear density, or LD, that you can see in previous video, that how we calculate linear density. And essential for understanding mechanical property. Why? Because in XRD, we need plane crystallography for slip and dislocations and plastic deformation we need, and many properties or mechanical properties that relate to Miller indices and planar crystallography. And what is PD that we need that for slip or dislocation? Is number of atoms in one plane divided by area of the plane. If you remember from LD, it was number of atoms in one directions divided by length of that directions. Okay. Family of the plane and directions. We talk about the family of directions, if you remember, today in previous video. And today we want to talk about the family of planes. You remember that for plane we use a parenthesis, but for family we use the bracket. Bracket HKL means a group of symmetrically equivalent plane connected by the crystal symmetry. For example, the family of 100. What's the meaning of the family? It means they are equivalent in crystallographic in, for example, planar densities, atomic packing, or something. Family in plane or families of plane allow simplifications, means physical phenomena such as sleep often affect all planes. We cannot say only affect this plane. For example, if we have, you see that I explained that how we find, it is the family of 111. Family of 111 in FCC means which planes? Means includes all of these planes. The first plane is 111. The next one is 1 minus 1, 1. The third one, for example, 1, 1 minus 1. Okay, so we have different plane that we can talk about that, and BCC and FCC that today we want to talk about that. The most close back planes or family of that for FCC is 111, and for BCC is 110. In this way, you see the yellow plane that is 111, and for FCC structures, yeah. What's the meaning of 111? If so, fast review what we talk about the Miller indices, for example, XYZ means intercept in x-axis as 1, y-axis at 1, z-axis at 1, yeah? Or AAA, that reciprocal of that, normalize that, or something, and reach us to 1, 1, 1. And if only we focus on this plane, it should be in this form, yeah? C is this point, B is this atom, A is this point, F is this atom, E is this, and D is this. Yeah, rotate that and you see in the plane view, planar view, it is the same as this or triangle that you see here. Okay. And again, it is 1, 1, 1 plane. But for BCC, we want to talk about the most close packed plane that is 1, 1, 0. I change the color of 1, 1, 0. What's the meaning of 0 here? Means parallel to z-axis, yeah? So the red one is this, 1, 1, 1, 1, 1, 0. It is the red one. Yeah? Okay. In this slide, we want to talk about planar densities for FCC and BCC. At the left side of this slide, you see FCC planar density for the most close packed family 1, 1, 1. You saw that in the previous slide too. It is the triangles A, B, C, D, E, F or something. Okay, it is 2R, right? It is R and it is R. So the total length of this is 4R. 4R, 4R. And all angle is 60 degrees, okay? For the area of triangle, we need to calculate height first. Okay. Look at here, this triangle. This triangle. What is this side? This side is 2R. What is this side is H, and what is this side is 4R. For the right triangles, we can say 2R squared plus H squared equals 4R squared. So you can find H here. After finding H, that for this case is 2R root 3, we substitute here. What is the area of the triangles? Height times base divided per 2. What is the base? 4R. What is the height? We calculate here 2R root 3 divided 2. This and this cancel each other. R is R squared root 3, 4R squared root 3. Okay, it is area. What is the planar density? Planar density for family 1, 1, 1. Number of atoms centered on 1, 1, 1 plane. Okay, I change my color again. Look at here. It is 1 per 6. It is 1 per 6. And it is 1 per 6. Okay. And change the color. Here. It is half. It is half. And it is half. So, how many atoms we have? The total atoms means 3, 1 per 6, 1 over 6, and 3 half is the number of atoms. So the number of atoms is half, 3 over 2 is 4 over 2 or 2. So the number of atoms centered in 1, 1 plane is 2 atoms. What is the area? We calculate that 4R squared root 3. 2 and 4 cancel out each other. 2R squared root 3. So if we simplify that as a function of R squared is 0.288 per R squared. If instead of R substitute as A, if you remember from FCC, in FCC root 2A was 4R, right? Or R is root 2A divided 4. If you substitute here, instead of R as a function of A, we reach to 4 divide root 3A squared. Okay. Now BCC and the most close packed plane, that is 1, 1, 0. You see the plane here. It rotates, that should be in this form. So in this triangle, we are looking Y, yeah. X is the lattice, is the A, lattice dimension. Z squared, if you remember from the BCC, Z is 4R is the most pack. 2R, R is 4R. So 4R squared minus A squared. And 4R was root 3A for BCC. If you cannot remember that, review the previous videos. And A is 4R per root 3. So it is A or X, yeah, X squared. Substitute here, we find Y. What is the area? X times Y is rectangle. And the area is 16R squared root 2 per 3. What is the planar density for 110? The number of atoms centered of this. Okay, I'll change the color. Here, it's a quarter. What is the number of atoms? 4 times 1, 4, and 1 at the center, 1, it should be 2. So again, number of atoms, 2 atoms, divided by this area. As a function of R, it should be 0.265 per R squared, that you compare that and you see it is PD111. In FCC is more close to PD110 as a R. And if you substitute R as A, you know that. What is the relation between R from here? Is root 3A per 4. If you substitute, you find root 2 per A squared. So PDD in 1, in FC structures is more than PD in 110 in BCC structures, means more close back. Okay. And this slide, we want to talk about that FCC slip systems. This bracket means the family of 111, and if it is the family of directions of 110, if you remember. We have 4 unique 111 planes in the cube, that one of them you see here, 111, but we have family of that. I talk about that means rotate that, the sign different or something. One of them is -11, another, for example, so I write for you. 111, -11, 1 -11, 1 1 -1. Okay, so we have 4 planes in this family. Each of them has 3 directions. I show the direction. The first one by red, it showed here. What is this direction? It is 1 -1 0. And you remembered from previous videos about when we talk about the directions, family direction or something. So the coordinate of this point minus this point, if you remember. Okay, the another directions that we have, the green one, yeah, it is 0 -1 1, yeah. And the next one is the orange one. That is 1 0 -1. So we have 4 planes. For each planes, we have 3 directions that the most closed packed means the maximum LD related these 3 directions, the maximum PD related these 4 planes. So we have 4 planes in the cube, 111. Each plane contains 3 unique directions, the family of 110 that I showed all of these directions. 4 times 3, we have 12 equivalent slip systems. Having many slip systems means FCC metals such as aluminum, Cu, nickel, Au, or gold are very ductile because they can deform plastically in many orientations. Yeah. Yeah. I hope that you enjoyed this video, and this video helped you understand the topic better. As a special thank you, I have created a free study guide with everything. Today we talk about that. And to get your copy, just find the link in the descriptions. Your feedback helps me improve these lessons. Please leave the comment if you have any questions, and subscribe for don't miss upcoming videos. Thank you so much, and bye.